The content in this video can be found on pages 47 through 49 of your textbook and is meant to help you achieve learning objective number 9, which is to describe what happens to incoming solar radiation using a diagram such as the one shown here or the one in figure 216 in your book. If you haven't already done so, it's a good idea to skim pages 47 through 49 before you watch the rest of the video, paying particular attention to the bold words and to the figures and their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for the chapter. When incoming solar radiation enters the atmosphere, three different things may occur simultaneously. First, air which is transparent to certain wavelengths of radiation may simply transmit energy, allowing it to pass through without redirecting or absorbing it. Second, some of the energy may be absorbed. Recall that when radiant energy is absorbed, the molecules begin to vibrate faster, which causes an increase in temperature. The third thing that can happen is that some radiation may bounce off of the gas molecules or the dust particles in the atmosphere without being absorbed or transmitted. What determines whether solar radiation will be transmitted to the Earth's land-sea surface, absorbed by the gases and particles in the atmosphere, or scattered or reflected by those gases and particles? As you'll see in this presentation, it depends greatly on the wavelength of the radiation, as well as the size and nature of the intervening molecules. Transmission is the process by which shortwave and longwave energy pass through the atmosphere without interacting with the gases or other particles in the atmosphere. About half of the incoming solar energy that reaches Earth's surface is transmitted by the atmosphere. The remainder is redirected by gas molecules and particles in the atmosphere and arrives as diffused light. Figure 215 illustrates what happens to incoming solar radiation averaged for the entire globe. Notice that on average, about 55% of incoming radiation reaches the Earth's surface. About 50% is absorbed at the surface, and the remaining 5% is reflected back towards space. The amount of absorption, on the other hand, the amount of energy absorbed by an object depends on the wavelength or the intensity of the radiation and the ability of the object to absorb, which is known as the absorptivity. In the visible range, the degree of absorptivity is largely responsible for the brightness of an object. Surfaces that are good absorbers of all wavelengths of visible light appear black in color, whereas light-colored surfaces have a much lower absorptivity. That's why wearing light-colored clothing on a sunny summer day may help you keep cool. Although Earth's surface is a relatively good absorber, the atmosphere isn't. As a result, only 20% of the solar radiation that reaches Earth is absorbed by gases in the atmosphere. The atmosphere is a less effective absorber because gases are selective about the wavelength of radiation that they absorb. Freshly fallen snow is another good example of a selective absorber. Snow is a poor absorber of visible light, reflecting as much as 90% of it. And as a result, the temperature directly above a snow-covered surface is colder than it would otherwise be because much of the incoming radiation is reflected away. By contrast, snow is a very good absorber of infrared heat radiation that's being emitted from the Earth's surface. As the ground radiates heat upward, the lowest layer of snow absorbs that energy and radiates most of it downward. Thus, the depth at which a winter's frost can penetrate into the ground is much less when the ground is snow-covered than in an equally cold region without snow. Giving credence to the statement that the ground is blanketed with snow, farmers who plant winter wheat desire a deep snow cover because it insulates their crops from bitter winter temperatures. Reflection is the process whereby light bounces back from an object at the same angle and intensity at which it was received. By contrast, scattering is a general process in which radiation is forced to deviate from its straight trajectory. When a beam of light strikes an atom, a molecule, or a tiny particle in the atmosphere, it can spread out in all directions. Scattering disperses light both forward and backward in a process called backscattering. Whether solar radiation is reflected or scattered depends largely on the size of the intervening particles and the wavelength of the light. The amount of radiation expressed in a percentage that is reflected by an object is called its albedo. The figure here gives the albedo for a number of different surfaces. So fresh snow is 50 to 90%. Fresh snow is 90% reflective. So when we have thick clouds, they can do as much reflection as fresh snow in many cases. The high reflectivity of clouds can be observed when looking down on clouds during an airline flight. By contrast, dark soils and parking lots have low albedos and thus absorb much of the radiation they receive. In the case of a lake or the ocean, note that the angle at which the sun rays strike the water greatly affects the albedo. So this reflection can be anywhere from 5 to 80%, depending on whether the sun is high in the sky at noon or whether it's a sunrise-sunset situation and the incident light is at a very low angle. Earth's total albedo, which is called the planetary albedo, is 30%. That energy is lost to Earth and does not play a role in heating the atmosphere or the Earth's surface. The amount of light reflected from Earth's land-sea surface represents a small percentage of the total planetary albedo. Not surprisingly, thick clouds, which have high albedo, are largely responsible for most of Earth's brightness as you see it from space. The moon, which has neither clouds nor atmosphere, has an average albedo of only 7% compared to Earth's 30%. Although a full moon appears bright, the much brighter and larger Earth would, by comparison, provide far more light for an astronaut's Earth-lit stroll on the moon. Although incoming solar radiation travels in a straight line, small dust particles and gas molecules in the atmosphere scatter some of this energy in different directions. The result, called diffused light, explains how light reaches the area under the limbs of a tree, and how a room is lit in the absence of direct sunlight. The two factors that produce Earth's blue skies and red sunsets are the preferential scattering of solar radiation by atmospheric gases and the amount of atmosphere through which the sun rays have to travel before they reach the Earth. Remember that sunlight appears white, but it's actually composed of all the colors of the rainbow. Atmospheric gases scatter shorter wavelength light in the blue and violet range more effectively than they scatter longer wavelength light in the red and orange range. Because shortwave radiation is preferentially scattered, when you look in any direction away from the direct sun, you observe the short wavelength blue light. So that's these wavelengths, giving most of the sky that blue color. In contrast, the moon and Mercury, which are without atmospheres, have dark skies and pitch black shadows, even during daylight hours. Overall, about 1/2 of the solar radiation that's absorbed at Earth's surface arrives at diffused or scattered light. We can see the effects of color separating too in sunrises and sunsets. So in this cartoon, you can see somebody standing out under the sunlight at noon. And he or she perceives that sunlight as white because all of the waves of visible sunlight strike our eyes. At sunrise and sunset, the white light from the sun passes through a thicker portion of the atmosphere. So here's the thickness for the noon sunlight, and here's the thickness for the sunset. Okay, so a much longer path through the atmosphere. The scattering of light by air molecules removes the shorter waves, the blue light, from the beam, leaving longer waves of red, orange, and yellow to pass through. So the sky is blue because air molecules selectively scatter the shorter wavelengths of visible light, green, violet, and blue, more effectively than longer ones. When those shorter wavelengths reach our eyes, we see the blue. On a clear day when we look up, blue light strikes our eyes from all directions, making the sky appear blue. On Earth, the most spectacular sunsets occur when large quantities of tiny dust or smoke particles penetrate the stratosphere. For 3 years after the great eruption of the Indonesian volcano Krakatau in 1883, brilliant sunsets occurred worldwide. In addition, the European summer that followed this colossal explosion was cooler than normal, which has been attributed to the loss of incoming solar radiation due to an increase in backscattering. And the human effect of that event was enormous. 1883 was a bad year for crops. Back in the 1700s, we had another big Indonesian volcano erupt, and we had big crop failures all across New England, and it was known as the year without a summer. 4th of July in some parts of our country, snow was falling from the sky. Large particles associated with haze, fog, and smog scatter light more equally in all wavelengths. Because no color predominates over any other, the sky appears white or gray on days when large particles are abundant. Scattering of sunlight by haze, water droplets, or dust particles makes it possible for us to observe bands or rays of sunlight called crepuscular rays. These bright fan-shaped bands are most commonly seen when the sun shines through a break in the clouds, as you're seeing in this figure. Crepuscular rays can also be observed around twilight when towering clouds cause an alternation between light and dark bands to streak across the sky. Use the course content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped by any of these questions, start a discussion on the Canvas site or ask me for help.